Thank you very much for inviting me to give this presentation at this EPIC event. And I will talk about, computing for AI. And I will try to highlight several aspects of this. Indeed, as Ivan mentioned, I'm 100% IBM, but also have an affiliation with the University of Twente in the Netherlands, as you see indicated below. So I would like to start, let me see. Yeah, I would like to start with this picture. It's Roadrunner, the first petaflop supercomputer. It was built by IBM in 2008. So why do I show this picture? The interesting thing is, if you look at today's AI applications and the neural networks that are behind, and especially the training of these systems, then looking at the y-axis where you see the compute effort in petaflop second days and the evolution of these kind of systems over time, the x-axis, you see that today these AI networks, neural networks, need 10,000 days of a supercomputer that was installed the first time in 2008. This to indicate what a tremendous compute effort is related to optimizing, training the neural networks that we have today. You can look at, say, 2008. That's a long time ago. Probably it depends on your age, how long you think this is ago. I think it's not so long ago. So already that was a really strong supercomputer in 2008. And now we need 10,000 days of such a computer. So what are these computations that are required? If you look at the neural network, where in the picture you see these blue dots that are neurons, nonlinear activation functions. They are arranged in layers and are interconnected. On the interconnections, these lines, you see these yellow dots that are the synaptic weights. And in the end, in such a system, the neurons are all the same, the nonlinear functions. And the functionality is determined by the interconnections and the strength of all these connections. So in the end, the values of the synaptic weights. Now, if you look at one neuron, it will receive signals from all the neurons in the previous layer. And each signal is weighted. That means the signal is multiplied with a value. So that's a multiplication. And then all these multiplied values need to be added together. In the end, that is a multiply accumulate. And if you do this not for a single neuron, but for the full layer, this turns into a vector matrix multiplication. Now, the compute effort of a vector matrix multiplication scales with the number of neurons. And of course, you also have the calculation of the nonlinear activation itself, which clearly scales with the number of neurons. Whereas the vector matrix multiplication scales with the number of neurons squared, the square thereof, should have said. So clearly, if the size of these networks is increasing so tremendously, as we know that they do, with billions of parameters, it's clear that the vast majority of the compute that is required is, in the end, in vector matrix multiplication. So this is the thing that needs to be enhanced and made more power efficient in order to make the overall compute more powerful. Well, this is currently going on, this whole trend, with existing hardware. And what's happening is that transistors continue scaling. Say, some time ago, there was the feeling that Moore's law is going to end. Well, it did change in the fact that, say, the standard Dennard scaling is over. But currently, transistors continue scaling by adding in new geometries and new materials. We have the memory. That is, say, on the one hand, as you see on the right-hand side, memory and storage, as for example, DRAM or maybe hard disk and so on, but also the memory that is on the chip itself, like SRAM, the logic functions and the circuits, in the end, for example, to do the vector matrix multiplication. And as I said, all these things continue scaling. Transistors continue scaling, memory continues scaling in terms of, say, the amount of transistors per area, the amount of memory, say, capacity. And what's also changing is that the memory is assembled closer and closer to the point where you do the calculations in the accelerator or in the CPU. So in the past, as you probably remember, memory was integrated as these vertical DIMMs on a compute board. Nowadays, memory is integrated as an HBM, high bandwidth memory, which is a vertical stack of DRAM, 3D integrated, directly on the same carrier substrate as the CPU or the GPU or the other accelerator. And the other thing that is happening, of course, to continue to scale the system is the communication between all the parts of the system, higher connectivity bandwidth at all levels, and here optics is playing a more and more important role. Nevertheless, while all these trends continue going, there is a discrepancy that is appearing, and that's what I want to show here. The important discrepancy is that the compute in flops, as you see indicated in the graph on the lower right, is scaling still much faster than the communication bandwidth, for example, to memory or the overall interconnection. So the compute effort is scaling as 60,000 times last 20 years, the memory bandwidth 100 times, and the interconnect bandwidth even less. So there is a change, a shift in the overall architecture. And this needs to be tackled. Let's look back to 2011 related to optics. As this is an optics conference, this is a slide I was showing in 2011. And what you see indicated here is a compute board with processors, with memory. In 2011, this was this vertical memory, and the way how optics is integrated. I started with 2008, which is again this Roadrunner system, because this was not just the first petaflop system, it was also the first system where optics was massively integrated by plugging it at the edge of the card as pluggable optics. Then in 2011, IBM built a system called Perks, which was a supercomputing system where optics was integrated not just at the edge of the system, but in the system itself on the processor package, as you see indicated there. And at that time, long time ago, I would say, we already had a roadmap to continue this integration of optics, going to a deep integration of optics on the processor package, the communication in the board, in the backplane, and this trend moving forward, going maybe from, say, VCSEL-based systems to silicon photonics and so on. In the end, a trend of, say, bringing optics closer, the integration of optics closer to the way how we are integrating electronics already, right? But what happened? Nothing. In the end, this system in 2011 was a massive exploration and also demonstration of the capability of optics, but the integration thereof in compute systems at that time was viable for a supercomputer, but too expensive for standard systems. So this whole trend at that moment did not happen. But now we are in a different situation with the whole scaling of compute requirements related to AI. So this whole story of bringing in optics in the system for communication is coming back. And IBM is working on this. There was a press announcement last year. The important thing here is that we need to learn from the past and bring the optics in such a way that we overcome the massive overhead that optics used to bring in terms of, say, assembly, number of components, fiber handling, and so on. And one way how IBM is tackling this is by enabling a direct dense optical I/O and fiber coupling to a silicon photonics chip with a polymer waveguide interface, as you see indicated here. Now, if we do this, this will help continue scaling compute systems. But we will not come around the standard bottleneck that we have, which is the von Neumann bottleneck, that if we do not change the compute architecture, we continuously need to move data from the processing unit to memory and back. So looking at this, say we have main memory, like DRAM, local memory, SRAM, the processing unit. If you look at, say, the energy it takes to bring the data from main memory into the processing unit, what you see here is that it's especially the transfer of data between main memory and the local memory that takes most energy. So this is something we need to try to get around. And this is where in-memory computing and analog AI is coming in. We want to go to a situation that you see on the right-hand side. And I explain it here, first of all, in the electrical domain. We want to do signal processing in a way that resembles more the actual calculation in a neural network. And imagine you have, for example, a resistor. You apply a voltage over a resistor, then the current you get is the voltage times 1 over the resistance, so the conductance. You can do this for one resistor or for a lot of resistors, and then take all these currents and bring them together to one output. And in the end, you use then Ohm's law and Kirchhoff's law to do exactly the calculation that we know from the neural network. And in this case, the compute effort does not scale with the square of the number of neurons as in the digital case, but it's in this analog case, it scales order 1. So whether we have just a few resistors, a few synaptic rates, or a lot of them, we apply the voltages and we immediately get the output. Now, you can do this in the electrical domain, and I will say a little bit more about that, but also in the optical domain. And say a similar approach you can think of as, for example, the reflection of a light beam on a mirror. The output is the input power times the reflection, that's the multiplication. You can do this with many mirrors and many beams and bring all the outputs onto a detector, and you have the same kind of effect. Important, if you do this, is that you need to resemble the full architecture of your neural network into the hardware. But should avoid to reprogram this, say, analog structure, because then you would still need to read data from memory, reprogram, and so on. You want to say map the full neural network into the hardware, as you see indicated below, because this way data can nicely flow through without any memory access, because the data is coming in. You have all these synaptic rates already programmed in your accelerators, in your analog accelerators, and you massively avoid actual memory access compared to the digital case. And this way you can win several orders of magnitude for inferencing neural networks and for training even more. So the whole system then looks roughly like this, much simplified. Now, how do we do these accelerators in the electrical and in the optical domain? In the electrical domain, it is clear that there is this architecture, as you see indicated on the left-hand side, which is a crossbar array, where you have these lines that are, say, conductive lines, copper lines integrated in the back end of line of a silicon process that are crossing. And at the cross points, you have this resistive element. Now, the important thing is that this resistor must be programmable to the value that you need related to the synaptic rate in the neural network. So you need a memristor. That's a device where you can set the value of the resistance with, say, a larger voltage, 1 to 2 volt. And when you read it out at 0.1, 0.2 volt, it doesn't change. So it's a non-volatile resistive memory that should be able to take multiple resistance levels. Well, there are various technologies available here. What is clear is that it's always this crossbar type of architecture, the different technologies to realize the memristor, like phase change memory, resistive RAM, ferroelectric RAM, and I will give you an example. In integrated optics, it looks slightly different. You can use different kinds of integrated optic architectures, circuit layouts, in order to build this kind of functionality. On the left-hand side, you see a crossbar, similar as in the electronics. You can also do this with a kind of Mach-Zehnder interferometer structure, or with a diffractive element, as you see fully on the right-hand side. I will say more about this later. Let's first talk to also say, compare what optics can do with what electronics can do, let's first have a look at an example of the electrical situation. We have been working at IBM on resistive RAM devices that are, as you see indicated here, metal, insulator, metal kind of structures. The metals in the structure are this titanium nitride layers. And in between, we have a thin hafnium oxide layer and the titanium layer as a kind of base technology that has been known for a long time. And if you have realized this structure, in the beginning, the resistance is very high. You apply a voltage in order to get a controlled breakdown and create a conductive filament in the hafnium dioxide that's indicated with this red line. The issue of this standard technology is that you get this conductive state, you can reverse the voltage, and you can then open this conductive filament again by getting tunneling. So you go back to high resistance, but because it's a tunneling related effect, this is something that is very stochastic and very strongly depends on the actual configuration of your atoms in the whole structure. What we've been working on then in my team at IBM is that we have replaced this titanium layer with a metal oxide layer. The idea here is that this conductive filament is in the end is a line of oxygen vacancies. And these the oxygen goes into the titanium on the standard technology side. What we were hoping is that if we have a metal oxide where if the metal oxide is more metal-like, you have a high conductance. If it's more oxidized, you have a high resistance. Maybe we can say make this technology this way more gradually changing the resistance by step oxidizing or reducing the metal oxide layer. So we've realized this type of technology, and what you see indicated here is that indeed this is the case. What you see indicated in the graphs at the bottom is that we have the technology, we have formed these devices in such a way that you can actually switch the resistance. So we have already created this filament. And then we come in with a series of either positive or negative voltage pulses. You see on the left-hand side that for the standard technology, you have a very stochastic kind of switching behavior and very abrupt switching from a low to high resistive state. In our new technology, this is much more gradual. And on the picture fully at the right, you also see that if we stop the, say, providing the positive or negative voltage pulses at some point and just measure the resistance over time, that it does stay very stable. So indeed, we have here with this new technology, we have something that is capable to represent a large range of resistances, so a large range of synaptic weights, which is non-volatile, exactly what we need for the inference, but even in this case, also for the training of neural networks. We have optimized this technology further. We have transferred this technology also to IBM Albany, which is a kind of development foundry from IBM in the US. And what you see indicated here on the in the second graph is that we are now able, after optimizing this technology, to program up to 35 levels. They are nicely stable over time. And we have also, in the graph on the fully right-hand side, we have looked how these kind of resistances behave over time, extrapolated up to 10 years, and we see that we can store up to 10 levels, resistance levels, even after 10 years. Now, what is important with this type of technology is that it is very, very dense. We can scale these devices down to 70 by 70 nanometer. They are integrated in the back end of line of a standard silicon process, so you can directly combine this kind of functionality of doing these calculations, the vector matrix multiplications, with CMOS electronics that's integrated in the front end. So with these kind of structures, you can, in the end, realize a fully mapped neural network in hardware, as I've indicated before, on a silicon chip. We have demonstrated through simulation that this technology can be applied. This is a collaboration with the University of Eindhoven and BMW in the EU project Fast Track, that we can use this technology for for example, gesture recognition for human car interfacing. We can use it for training neural networks as well as for inference, and that the accuracy that we get is roughly the same as using floating point digital technology. So that's the electrical side. Let's have a look at the optics. So as indicated, there are several options in the optics, and I want to show you a few examples. One is to do the crossbar directly in the optical domain. You can do this, but different than in electronics, where you can bring together two currents and they nicely add up, Kirchhoff's law. In optics, this does not work. Because if you try to combine signals, you always have an interference effect, and in the end, you will lose a factor 1 over n. If you want to couple in light, also light will be coupled. So this is an inherent challenge of these kind of structures. So we have realized these kind of designs and we've tested, and this is all working, but there is a scalability issue because when you lose 1 over n of your power, it's very hard to scale these kind of matrices. So from that point of view, doing such an interference kind of option, a coherent situation, as indicated here, using such a, say, Mach-Zehnder interferometer kind of structure is much better. But here in the end, you run into challenges because the number of heaters that are required scales up quickly, or heaters tuning elements to set the interference conditions scale strongly with the number of inputs and outputs. So here in the end, you run into a challenge in terms of, say, the complexity to control the system. What we did is that we've realized a simplified version of this, not a two-dimensional kind of interferometer structure, but more a one-dimensional. It's a cascade, linear cascade of Mach-Zehnder interferometers, as you see indicated below. And if you use such a structure in the time domain, you can build a convolutional signal processor. You see more details here. What happens is that we have a cascade of, say, tunable couplers, tunable delay lines, and if light is coming in, for example, from an image, you have the first pixel, the second pixel, data is coming in a time sequence. If the first pixel value, the part of the light that is going through the long arm, will meet the second pixel, the light fraction thereof that is going through the short arm in the delay line, you get an overlap. And this way you can in the end do a convolution, because this is a finite impulse response filter, which is in the end representing a convolution. And convolutions are very important in neural networks. So this type of device can in the end do a convolution for neural networks and convolutional neural networks. For example, for, as I indicate here, for edge detection. We have realized these devices in silicon photonics. And by doing these operations, as you see on the right-hand side, if we have a signal that's coming in that is increasing the blue line over time in strength, the red line is the output, and you see that we can detect the edges and in the end, in an efficient manner, get an operation that is important for neural networks. If we now do the calculation on the efficiency, as you see indicated here, taking into account the full system, the laser, the modulator, the data that needs to come in, the driver for the modulator, the photonic processor, including, say, all these Mach-Zehnder interferometers that need to be tuned to the right value in order to represent the operation you want to do, the detector, amplifier, and so on. Also taking into account the full optical power budget to make sure that in the end we are really able to detect the signal at the end with the required accuracy or resolution. If we take all these things into account, we come to an overall efficiency of this device of roughly 2.5 teraops per watt, which is an interesting value because it's roughly the same type of efficiency you get for digital systems. So it's not inherently by using this kind of analog approaches that we massively win. So does this now make sense? The answer is, in order to win in power efficiency, in this case, not directly, but this system can do something that digital systems or electrical analog systems cannot do, in the sense that we can handle ultra high-speed signals. We can also reprogram this system, say, depending on the tuning elements that you use in a very fast and very accurate manner. So depending on the application, this is certainly something that can find a path. In the last few minutes, I see that my time is slowly coming up, also leaving time for questions. In the last few minutes, I want to say something a little bit about, say, applying optics for training neural networks. The application I just gave is for inferencing, the convolution calculation, but can we also use optics for training neural networks? The difference between inference and training is that in the inference case, you want to set your synaptic weights to a dedicated value, and it should stay there. Whereas if you do training, you are continuously optimizing your synaptic weights until your neural network is doing what you want it to do, until the error is minimized. Now, to do this in an efficient manner, these kind of crossbar structures, as I've explained before, are very efficient means, because you can do the forward calculation, just the inference operation, as you see indicated on the left-hand side in blue, as well as if you do the backpropagation algorithm, you can also do the backward calculation on the transpose of the matrix using the data in red, where you propagate the error back and you do the vector matrix multiplication on the transpose of the matrix. And you do this with exactly the same structure. So another important aspect here is that you change the values of your resistances just by applying the inputs at the of your signals at the two inputs that you have in your system. So, for example, X and WX, you just put them in. So, in the end, you use also just say order n signals to change n square weights. And the question is, can we do something similar in optics? And a photonic crossbar using diffractive structures is what you see on the right-hand side. Assume we have a medium where we can write in a certain corrugation of the refractive index in such a manner that we have are able to do, a diffractive coupling of an input to an output, and then also tune this diffractive coupling efficiency. This can be done using the photorefractive effect. The photorefractive effect, as you see in the center, is a nonlinear optical effect where, in the end, through the excitation of carriers and a redistribution thereof in a medium, you're able to store a synaptic weight in the optical domain, because this material also has, an electro-optic effect that in the end transfers this redistribution of charge carriers in a change in the refractive index on which you can do the synaptic weight operation. So this is not new. This is something that people already did a long time ago in the 90s. Now, with integrated optics, we can do this in, for example, silicon photonics. The thing is, we need to integrate a photorefractive layer. We've done experiments here, just finalizing, using, different types of materials, building these structures, as you see indicated. We have demonstrated this effect on gallium arsenide, and we are currently exploring how to bring this further. The experiments we did here is showing that we can do the synaptic operation using 2 optical inputs. We need to scale to more. That's what we are currently going towards. And I would like to finalize in the end with, a comparison with all these operation circuit layouts. The crossbar where you have the input, where you have the loss issues with scaling 1/n. The interferometric structure, where you have a scalability challenge because you just become too complex in controlling the structure, or a diffractive structure, as I just indicated, where we believe in principle you can scale to a much larger number of inputs and outputs. And the latter is important because if you have many inputs and outputs, that means that you have a lot of calculations between the input and the output, and your, say, base effort in terms of, for example, power that you need to give in always the laser and the detector, the amplifier, and so on. That is a given that you have. If you can do more calculations in between, you win in efficiency. And based on our calculations, if you are going to a large kind of crossbar in the analog domain, you can actually win. So with this, I would like to conclude stating that electronics has an advantage in terms of scalability, going to very dense structures. Optics is good because you're able to handle very high-speed signals. And depending on the application, you have to see what makes more sense. With that, I would like to thank the team and thank you very much for your attention.